Let's start once again. Let me see whether the recording is on or not. Yes, so the recording is also in the on mode. So let us see. Up to here we had already learned 2 hours ago, right? Up to here we had already learned. So let us see now this particular concept, that is nuclear magnetic moment, about which we are going to learn in the upcoming classes. We are going to learn in very much detail about this nuclear magnetic moment. Okay, in the upcoming classes it is going to be covered in detail. And if someone amongst you has already learned atomic and molecular physics, then he or she might find this particular concept very easy. Okay, but I haven't taught atomic and molecular physics in my particular YouTube channel, so that's why I am just giving you a quick go through of nuclear magnetic moment. It will be covered in this series itself. It will be covered in very much detail in the upcoming classes. But for the time being, I am just uh, uh, passing by this particular term, so that you guys don't feel difficulty in the upcoming classes. Although in the future classes in this particular series itself, this particular term will be taught in very much detail. Okay, very much detail. So nuclei do have magnetic dipole moments. You This is a quite general statement. Okay, nuclei do have magnetic dipole moments. They arise from the intrinsic magnetic moment of protons and neutrons in the nuclei. Okay, so how do these magnetic dipole moments arise? These magnetic dipole moments arise from the intrinsic magnetic moments of protons and neutrons in the nuclei. Okay, why? Because nuclei contains protons and neutrons. Okay, what are the constituents of nucleus? Neutrons and protons are the constituents of nucleus. So if nucleus has magnetic dipole moment, then obviously this magnetic dipole moment will be on account of protons and neutrons. Okay, so this magnetic dipole moment arise from intrinsic magnetic moments of protons and neutrons in the nuclei. Okay, so intrinsic magnetic moments of individual protons and neutrons, that in total constitutes the magnetic dipole moment of the nuclei. Okay, so they arise from intrinsic magnetic moments of protons and neutrons in the nuclei and from the current circulating in the nuclei due to motion of protons. Okay, so how do this magnetic dipole moment of the nuclei arise? It arises from the intrinsic magnetic moments of protons and neutrons in the nuclei and from current circulating in the nuclei due to motion of protons. Okay, you know this very well, that neutron is chargeless. Okay, so that's why the current will be constituted only because of protons. Okay, because neutron is chargeless, so only proton will constitute the current. So from the current circulating in the nuclei due to motion of protons. Okay, so that's why only protons has been written over here. So intrinsic magnetic moment of protons and neutrons and current circulating in the nuclei due to motion of protons, these are the two factors. Okay, so how the magnetic dipole moment of nuclei, what does it comprise of? Okay, I am talking about magnetic dipole moment of nuclei. What does it comprise of? So it comprises of intrinsic magnetic moment of protons and neutrons. Okay, it comprises of intrinsic magnetic moments of protons and neutrons, and okay, and what? And the current circulating in the nuclei due to motion of protons. Okay, so current will not be constituted by neutrons. Why current will not be constituted by neutron? Because neutron is chargeless, and you know this very well, that current is constituted only when a charged particle is in motion. Okay, current is constituted only when a charged particle is in motion. So the current will be constituted only because of protons, not neutrons, because neutrons are chargeless, proton has charge. So if proton moves, current will be constituted, but if neutron moves, current will not be constituted because neutron is chargeless. Okay, so that is the thing. So and from current circulating in the nuclei due to motion of protons. So magnetic moment of a nucleus is given as how is it given? I am just writing the formula over here. In the upcoming lectures you will get a better picture of this particular term. Okay, the better picture of this particular term you are going to get in the future lectures or in this particular series itself. Okay, and the atomic and molecular physics, when I will teach you, okay, whenever in the future when I am going to teach you that, then all these terms will be even more clearer to you. They will become crystal clear after that. Okay, so don't worry about it. So magnetic moment of nucleus is given as mu vector equal to gi into E divided by 2 times mass of proton. What is this? E means charge of proton. Okay, E means charge of proton. I vector. Okay, equal to I vector has its usual meaning which you have already learnt, right? What is the meaning of I? Total angular momentum vector. Okay, so I is your total angular momentum vector, gi is your Land's splitting factor. Okay, what is Land's splitting factor we are going to learn in the upcoming classes in detail, so don't be worried about it. So mu vector is equal to gi E divided by 2 mp I vector. So gi, when I multiply and divide this particular term by h cut, what do I get? I get something of this kind, gi, that is Land's splitting factor, E, that is charge of proton, h bar divided by 2 times of mass of proton. Okay, I vector, that is total angular momentum vector. Okay, I is what you can see over here, total angular momentum vector. Okay, so I vector is total angular momentum vector and divided by h bar. Okay, so that is the thing. Now this particular term is your nuclear magneton. Okay, E h cut divided by 2 mp, this particular term E h cut divided by 2 mp, this is your nuclear magneton. Okay, mu n. Okay, so I will substitute this particular term by mu n. Okay, and that will be your nuclear magneton, the value of which is given like this, 5.05 into 10 to the power minus 27 ampere meter square. Okay, am square means ampere meter square. Okay, 5.05 into 10 to the power minus 27 ampere meter square, that is the nuclear magneton, that is mu n value. Okay, so I have substituted this particular term with this thing over here. Okay, so mu vector is equal to Land's splitting factor into nuclear magneton multiplied by total angular momentum vector I divided by h bar. Okay, that is h bar is what? Reduced Planck's constant. H bar is what? H bar is h bar or h cut, whatever you may call it. Okay, so h cut is your reduced Planck's constant. Okay, h cut is reduced Planck's constant. So Land's splitting factor is given something like this. Okay, about which we are going to learn in upcoming classes in very much detail. Okay, what is this Land's splitting factor, etc., etc., we are going to learn in very much detail. But 1 by 2 gl plus gs plus 1 by 2 gl minus gs l into l plus 1 minus s into s plus 1 divided by I into I plus 1. Just remember the facts as it is for the time being. For the time being I am saying. Okay, for the time being remember the facts as it is. In the upcoming classes they will be very much clear to you. Okay, everything will be very much clear to you in the upcoming classes. You will have to follow the series very sincerely. Okay, so magnetic moment of neutron. Now let us see this particular thing, magnetic moment of neutron. Now you know this very well that neutron is chargeless. Okay, so someone might feel that it has no magnetic moment, but that concept is wrong. Okay, the concept that chargeless particle do not have magnetic moment, that particular concept is wrong. And why it is wrong, we are going to see it now. Neutron should not have magnetic moment because it has zero charge. Okay, neutron, if someone thinks very flatly, okay, if someone is not thinking very deeply, he or she is just thinking superficially, then that person might feel that neutron should not have magnetic moment because it has zero charge. Okay, so neutron should not have magnetic moment because it has zero charge. That is the thing which he or she might think. Okay, in fact magnetic moments depend upon current rather than charge. Okay, so that I am telling the fact that magnetic moment depend upon current rather than charge. Okay, magnetic moment do not depend on charge. Even if a chargeless particle is producing current, then magnetic moment might be created. Okay, because I am going to tell you according to Cork model also, the neutron, what is a neutron? Neutron has positive and negative charges equally distributed. Okay, if you look at the Cork model, if you have ever learned the Cork model in your BSc or engineering, whenever you might have learned physics, during those days if you have learnt about the Cork model, then you must be knowing this thing that neutron is composed of 3 quarks. Okay. So inside the neutron, according to quark model, the positive and negative charges are equal. That's why neutron is overall 0 charge. Okay. Why neutron does not have charge? Because the quark distribution inside the neutron is such that inside the neutron is such that the overall charge of neutron is 0. Okay. So in fact, magnetic moment depend upon current rather than charge. Okay. So although we are going to learn about the quark model later on, we are not considering the quark model right now, but we will explain the magnetic moment of neutron based on YUKAWA'S MESON field theory. Okay. Based on YUKAWA'S MESON field theory, we are going to learn why magnetic moment is there in neutron. Okay. So in fact, magnetic moment depend upon current rather than charge. Okay. So on what factors does magnetic moment depend? So magnetic moment depends on current. Okay. It does not depend on charge. Okay. Even if someone has 0 charge, even if something such as neutron has 0 charge, even then if it constitutes the current, then it will have magnetic moment. Okay. So for example, hydrogen atom has no net charge. Okay. In atomic and molecular physics, this particular example suits very much. Okay. Over there also we have such a condition. In atomic and molecular physics also we have such a condition. Okay. So for example, hydrogen atom has no net charge. Okay. What does a hydrogen atom comprise of? What does a hydrogen atom comprise of? It comprises of a positively charged proton at the center and an electron which is there around the nucleus. Okay. So one proton and one electron is what is hydrogen atom. Okay. So hydrogen atom has no net charge but does have a magnetic moment. Why does it have a magnetic moment? Because it constitutes current, right? It constitutes current. Thus neutron cannot be supposed to have magnetic moment if it contains equal positive and negative charges which are in motion. Okay. So neutron can be, can be. Okay. Thus neutron can be supposed to have magnetic moment. Okay. If it contains equal positive and negative charges which are in motion. So if neutron has equal positive and negative charges which are in motion, so neutron can also be supposed to have magnetic moment just like hydrogen atom. Hydrogen atom has no net charge. Okay, it has a positively charged nucleus, +1 charge in the nucleus, that is single proton in the nucleus, and there is electron which is there around this particular proton. Okay, which is moving around this particular proton. But hydrogen atom has no net charge. Okay, because positive charge of the proton and +1 charge of the proton and -1 charge of the electron, that gives overall charge to the hydrogen atom as being equal to 0. Still it has magnetic moment because it constitutes current. Okay, so similarly we can consider neutron to be formed out of equal positive and negative charges which are in motion. Okay, so neutron might also have, although it has net charge 0, still it can be supposed to have magnetic moment if it contains equal positive and negative charges which are in motion, right? So that is the thing. According to YUKAWA'S MESON field theory, now let us understand what is this YUKAWA'S MESON field theory, and let us understand the magnetic moment of neutron with this YUKAWA'S MESON field theory. Okay. According to YUKAWA'S MESON field theory, a neutron transforms into a proton and a pi meson or pion. You can also call it pi meson, can also be called as pion. Okay, you can also call it pion. Okay, so a pi meson or pion, whatever you might call it. So according to YUKAWA'S MESON field theory, a neutron transforms into a proton and a pi meson for a very short interval of time. So neutron is transformed into a proton and a pi minus meson. Okay, pi minus meson. Why negative charge? Because plus minus equal to 0. Okay, so charge has to be balanced. Charge on both the sides of the equation, has to be balanced. So that's why neutron will be converted into a positively charged proton and a negatively charged pion. Okay, and this pion has a very low mass, proton has very high mass, and neutron too has a very high mass. So this pion which will be ejected which will be ejected out of this neutron, this pi minus pion or pi minus meson. Okay, so this, since this meson is lighter than proton, okay, this pi minus meson is what? It is lighter than proton, right? So it is lighter than proton, its motion will be faster. Okay, the this meson, as it is lighter than proton, so its motion will be faster. So the motion of this pi minus meson will be faster. Okay, and resultant magnetic moment is that of revolving negative charge. Okay, now let me give you an example. This is, suppose your truck. Okay, this proton is what? It is like a truck, and this is like a ball. Okay, in classical mechanics you have learned all these things. Okay, in classical mechanics you have learned all these things, that something has a very huge mass and something has a very small mass, then the entire momentum is constituted only by the small mass, right? So this is like a truck and this is like a ball in front of a truck. So whenever collision, this is an example of collision only, right? So when neutron was moving and it got splitted into proton and pion, so pion will have very high kinetic energy as compared to this ejected proton, because pion has a very low mass. Okay, it has a very low mass. So this meson is lighter than proton, very much lighter than proton, so its motion will be faster, and resultant magnetic moment is that of revolving negative charge. Okay, so resultant magnetic moment will be what? It will be of this pi minus pion or pi minus meson. Okay, hence it is negative. Okay, so the resultant magnetic moment will be of a revolving negative charge, and hence that resultant magnetic moment will be negative. Okay, because negative charges make create negative magnetic moment, right? Negative charges create negative magnetic moment, so that's why this pi minus pion will create resultant magnetic moment, which will be a negative. It will also have negative value because the pi minus pion has a negative charge. Okay, so magnetic moment constituted by this pi minus pion will also be negative. Okay, proton and pi meson also possess a spin. Okay, this proton and pi minus meson, they also have spin and therefore have intrinsic magnetic moment. Okay, they also have spin, right? And therefore they have intrinsic magnetic moments also. Okay, resulting magnetic moment will be there, but they will also have intrinsic on account of their own spin. Okay, intrinsic magnetic moment means magnetic moment on account of spin about their own axis. Okay, intrinsic magnetic moment means magnetic moment on account of spin on their own axis, about their own axis. Okay, and therefore have intrinsic magnetic moments, that of a meson being larger. Okay, meson will have larger because it is lightweight, right? Meson will have larger because that is lightweight, so that of meson being larger due to small mass. This situation also contributes to a negative magnetic moment of the neutron. Okay, so both the things are constituting towards negative magnetic moment, that is the motion of pion around the nucleus, around the center of nucleus. Okay, see, this is the center of nucleus. Okay, and this is the shell. Okay, so when pion will be moving like this around the center of nucleus, then because of the motion of pion around the center of nucleus, that will create a negative magnetic moment, and the motion of pion about its own axis. Okay, motion of this pion about its own axis. Okay, motion of this pion about its own axis, that will also create a negative magnetic moment. Okay, intrinsic magnetic moment, negative. Okay, because it has negative charge and small mass. Okay, so this situation also contributes to a negative magnetic moment of the neutron. So the overall effect will be the proton, as it is very heavy, it will more or less remain much more in the same velocity. Okay, it will not contribute much to the magnetic moment. Proton will not contribute much to the magnetic moment because it has higher mass, so it will be basically what we can say, moving slowly. Okay, so it will not contribute much to the magnetic moment, right? So this situation also contributes to a negative magnetic moment of the neutron. Okay, so this particular situation also contributes to a negative magnetic moment of the neutron. So mu neutron is equal to minus 1.091 mu n. Okay, so this is what mu neutron means. Overall if you look at the neutron, then what will happen, this will contribute very high. So overall the magnetic moment of neutron will be negative because of this pi minus pion. Okay, so magnetic moment of the neutron is equal to minus 1.091 nuclear magneton. Okay, minus 1.091 nuclear magneton. Okay, so that is the magnetic moment of the neutron. Now let us understand with the help of this particular figure. So in the this is what is YUKAWA'S meson field theory, and how this is how YUKAWA'S meson field theory explains magnetic moment of neutron. Okay, how does YUKAWA'S meson field theory explain the magnetic moment of neutron? By the hypothesis that while revolving around the center of nucleus, okay, while revolving around the center of, this is the center of nucleus. So as the neutron is revolving around the center of this particular nucleus, the neutron is getting converted into what? The neutron is getting converted into a proton and a pi minus pion. Okay, so the neutron, this particular neutron got converted into proton and a pi minus pion. Okay, now this pi minus pion will again go like this. It will go like this and combine with the another proton and once again form the neutron. Okay, it will once again form the neutron. So this conversion from neutron to proton, this neutron converted into proton, and this proton, okay, this proton, or this proton, whatever you may call it, this proton or this proton, that is being converted into neutron. So this interconversion from neutron to proton and proton to neutron, this interconversion is continuously going on inside the nucleus. Okay, this interconversion from neutron to proton and then from proton to neutron, this interconversion is continuously going on while the nucleons are revolving around the center of the nucleus. Okay, this is what? This is the center of the nucleus which is hollow. Center of the nucleus which is hollow. Okay, so all these things are going on, right? Now as this particular particle is very lightweight, okay, it has a very less mass. Okay, so as it has very low mass, so it will constitute towards the negative magnetic moment of the neutron. Okay, so that is what has been explained in this YUKAWA'S meson field theory. So in the initial stage, the neutron itself produces no orbital magnetic moment. Okay, in the initial stage, the neutron was revolving like this around the center of nucleus. Okay, so in the initial state, the neutron itself produces no orbital magnetic moment. Okay, no orbital magnetic moment. Now in the intermediate stage, what happens? In the intermediate state, the neutron which was here, it got decayed into proton and pion. Okay, so it got decayed into proton and pi minus pion. Okay, or pi minus meson, whatever you may call it. So neutron decays to give proton and pi minus pion. Okay, or pi minus meson. Now this pi minus meson contributes to negative orbital magnetic moment. Okay, so this particular particle, as it was very lightweight, so its effect, its low mass effect, okay, because it had very low mass, so it had a very high kinetic energy because of that. Okay, because of being of very low mass, it had a very high kinetic energy. So it was having a very high kinetic energy, and this particular thing was having a very low kinetic energy. So as it was moving with a very high velocity, and this particular particle was moving in the opposite direction with a very low velocity, so the overall effect was such that this negative charge became dominant factor in deciding the orbital magnetic moment. This negative charge became the deciding factor in means the overcoming factor in deciding orbital magnetic moment. Okay, so neutron decays to give proton and pi minus meson, and pi minus meson contributes to negative orbital magnetic moment. Okay, pi minus meson contributes to negative orbital magnetic moment. Okay, this pi minus meson, what does it do? It contributes to negative orbital magnetic moment. Okay, so the overall magnetic moment of neutron is negative, that's why, because of pi minus pion. Okay, then in the final stage, the overall orbital magnetic moment of neutron is negative because of this particular pi minus pion. Okay, so in the final stage, this pi minus pion is absorbed by this another proton which was already there in the nucleus. So another proton absorbs this pi minus pion and gets converted into neutron. Okay, so in the final stage, pi minus pion is absorbed by core proton. Core proton means originally which the proton which was present originally in the nuclei. Okay, so this pi minus pion is absorbed by the core proton. So core proton absorbs this pion and gets converted into neutron. So the total number of neutrons and protons before the process and after the process, the total number of protons and neutrons before the process and after the process remain conserved, right? Because initially we had one neutron and one proton, and finally also we have one neutron and one proton. So the total number of neutrons and protons in the process remain conserved. But in the final stage, but in this intermediate stage, okay, in this intermediate stage, the neutron, when it was split into these two particles, that's what makes the neutron giving negative orbital magnetic moment. Okay, that's what makes the neutron giving negative orbital magnetic moment. Okay, so that is the thing. So we will learn about parity onwards in the next class, and hopefully everything was clear to you. And what I would like to tell you is that keep on reading books side by side. Okay, and you can rely on these lectures very much, and I will teach you in the next class. But please also join one coaching side by side, so that those people also teach you in a time bound manner. Okay, they will teach you in a time bound manner. Over here I am teaching what we can say, sometimes I will not upload video because I am very busy. So these things keep happening. Okay, so subscribe to this channel, and please do like the video, please give us thumbs up, please motivate us to make more and more videos. Okay, so thank you very much.